Hello everyone, my name is Chris Tomasi, I'm the team leader.
Justin Bustillo, I'm the graphics lead.
Ashley Foster, research analyst.
Luis Rivas, structural engineer.
We're JACL Engineering Solutions, and we built the I.C.E Thermosiphon, an innovative solution to improve solar panel efficiency and lifespan. Essentially, we're designing and building a system to passively thermoregulate solar panels from the backside, increasing efficiency and lifespan. The I.C.E Thermosiphon uses a closed-loop two-phase system with a radiator to absorb heat from the panel and expansion chamber to condense the vaporized liquid, which returns to the evaporator via gravity.
Elevated temperatures in solar panels are directly linked to efficiency losses and cell degradation. Here you can see the parameters of the solar panel we used in this project. The efficiency is 16.89%. This pertains to a temperature of 25 degrees Celsius. Every degree above that, we lose 0.38% efficiency. As such, our goal is to regulate the solar panel's temperature utilizing the back surface, increase efficiency, and extend the lifetime of the panel. Some of the key specifications we wanted in our project include a working fluid with a low vaporization temperature. We needed components all compatible with the working fluid, an airtight system we could depressurize to adjust the vaporization temperature. We wanted high conductivity between the panel and the radiator and a maximum weight of 16.5 pounds.
To get started, I'll take you on a quick tour of the design. Both of our panels were donated by 180 Solar and rest on our aluminum support structure. The structure has caster wheels on the bottom for added mobility. Next, we transition to the back side of the panel, where the aluminum support plates are located, supporting the expansion chamber and radiator. Taking a closer look at the expansion chamber now, you see the pressure gauge on the top left. Ball valves were used to pull a vacuum and drain the system, and male-threaded adapters connect to our 3/8-inch tubing down to the radiator. You can see the vapor travels up the riser to the expansion chamber, condenses, and returns to the radiator via gravity through the downcomer. This completes the circulating loop. Insulating foam presses the radiator against the solar panel backing.
Here are all of our assembly animations with figures labeling each component. Looking at the solar panel assembly in the middle, you can see the radiator being pressed against the solar panel by thermally insulating foam and an aluminum plate. Behind the radiator is a thin copper sheet to maximize heat transfer from the solar panel. Lastly, the final assembly shows the solar panel and expansion chamber assemblies mounting onto the support structure.
The radiator we're using has reservoirs at the top and bottom connected by thin vertical tubes. The liquid enters the bottom and the vapor travels to the top of the radiator where it exits at the barb tube connection. The vapor pressure of a fluid is the pressure the vapor exerts on the liquid surface. Lowering the pressure in a system lowers the vaporization temperature of the liquid. So using the Clausius-Clapeyron equation, we were able to determine that decreasing the pressure to 40 kilopascals lowered the vaporization temperature of our system to about 88 degrees Fahrenheit, which helped keep our panel cool since temperature remains constant during a phase change. This helped thermoregulate the solar panel. The latent heat of vaporization describes the amount of energy required to change the state from liquid to gas and vice versa. So our system takes advantage of the fact that phase change absorbs large amounts of heat. Over the course of our testing window, about 5 kilograms of liquid was vaporized and circulated through the system. The hydrostatic pressure in the downcomer drives that circulation. As the fluid in the radiator vaporizes, the pressure from the higher density liquid in the downcomer drives the flow. Using the hydrostatic equation, we found the pressure in the downcomer to be about 39 kilopascals. The submergence ratio or fill ratio is also an important parameter to drive the flow. This describes the ratio of the distance between the fluid level and the evaporator over the pump lift, which is the distance between the evaporator and condenser. We found the optimal submergence ratio to be about 0.72 for our system. Here's a comparison between the heat flux characteristics of a control panel on the left compared to a panel mounted with the I.C.E thermosiphon on the right. The takeaway here was that we transferred over 1,000 watts per meter squared with the thermosiphon, which translated to a net increase of 317 watts per meter squared. The heat absorbed by the evaporator needed to be removed by that condenser. So the current expansion chamber surface area and geometry moved about 140 watts per meter squared. Although the temperature drop from the expansion chamber or the expansion of the vapor also lowered the vapor temperature, there was about 870 watts per meter squared that still needed to be removed. It is recommended to add fins to the expansion chamber on future designs to increase the surface area, which would improve the system performance.
Here are our solar panels that we use for testing. They're made by Canadian Solar and they're resting on an aluminum support structure that we as a team fabricated here at the UTSA Makerspace. They keep the panels at 52 degrees and they're made mostly out of aluminum angles. Now Chris and Justin are going to talk about the I.C.E thermosiphon.
Alright, thanks Luis. See, if you come around to the back side of the panel here, you can get a better look at our system. Now what we've designed is on the other side of these plates and thermally insulating foam is a radiator, and that radiator is filled with liquid acetone. So as the solar panel heats up, it vaporizes the liquid inside the radiator, and if you come up here, take a look at the vapor line, you can get a shot of, you can probably see that in the video, the vapor rapidly traveling through this tube. What happens is, as the vapor goes up the riser into the expansion chamber, it condenses due to a change in volume and collects in the bottom. You can see it spurting out here, and this is traveling via the downcomer back to the bottom of the radiator. to complete the cycle. Essentially what we have is a naturally circulating passive loop that keeps our solar panel cooler than a control panel. Now, to prove that, Justin's going to take you through how we took temperature readings.
So we're using the temperature difference between our panel and the control panel to quantify the efficiency increase using our thermosiphon. So we're doing that using type K thermocouples on the back of each panel. There's 2 on the back of the control panel and there's 4 on the back of our panel. They're in the same location on each panel, and we're using the thermometers to keep track of those measurements. And on the front, using an optical pyrometer to take measurements on the same locations on each panel. There's 2 pieces of masking tape there. And lastly, we're using an anemometer to take ambient temperatures and wind speeds.
So here are some of the results from one of our performance tests. Over the period of 1 hour, our panel is on average 7.5 degrees cooler than the control panel. If the thermosiphon was expanded to cover the whole panel, this would translate to a 1.58% increase in power generation. As it is now, the efficiency increase wouldn't allow for our thermosiphon to pay for itself. However, the system could be optimized to cool to the ambient temperature by achieving greater depressurization and by switching to a fin expansion chamber with a larger surface area. Now here are some predicted profit calcs for a few systems where these optimizations are made. In these graphs, you can see the total lifetime profit of a 335 watt panel with no cooling and the profit increase you can get by cooling to or within 5 or 10 degrees of the ambient temperature. On the right, these profit increases are shown for a single panel, a residential 6 kilowatt system, and a utility 9 megawatt system. The cost of the components used in the I.C.E thermosiphon came out to just under $120. Once a system is designed that closely resembles the same model, mass producing this product would bring costs down drastically. So the potential for this product is exciting, especially for a 9 megawatt system.
In conclusion, the I.C.E thermosiphon kept the solar panel about 7 degrees cooler than a control panel under identical conditions, and adding a fin expansion chamber like we've been saying and lowering the vaporization temperature further would be quick changes that could improve the system performance. Overall, our opinion is I.C.E thermosiphon has a promising future.